Right, we're going to look now at the kinematics travel graphs, which should follow directly on from the work we've done at GCSE in both physics and maths. We're going to look at two types of travel graph, like we did at GCSE, the displacement time graphs and the velocity time graphs. At GCSE, you remember that when we looked at displacement time graphs, we talked about velocity being linked to gradient. You'll notice here we've made a distinction between two types of velocity. Okay, so if we consider this displacement time graph where we've got an object starting here, traveling away till it gets to its maximum displacement, and then it travels back to where it started again. And we'll use this graph to distinguish between average velocity and the instantaneous velocity at a point. Okay, now the average velocity is described as being the gradient of the chord between 2 points, change in displacement over time. Now that's actually the same definition as we used in the previous chapter. What do we mean by a chord? Right, if I consider this point here, so at this time the displacement is that one there. If I want to decide what the average velocity was between the beginning of the motion and this time here, if I want the average velocity over this time, that's the chord. That straight line there is the chord. So the average velocity would be this measurement divided by this one. However, if I wanted the instantaneous velocity, I want the gradient at a point. So if I wanted the actual velocity at that point, if I want the actual velocity at this point here, at this time, I would have to fit a tangent to the curve and work out the gradient of that line there. So average velocity over time will be the change in displacement divided by the time. Velocity at a point will be the gradient of the curve at that point. So let's have a look at, so if we go through the examples in the book, if you read the example, pause it now and read the example. So part A, how far from the lighthouse does the boat start? At the beginning, the displacement is 50. So A is 50. B, describe the displacement of and the velocity, how they change. Right, let's have a look at this. So we've got the displacement increasing to 650, but we notice that the gradient of a line gets less until the line is flat between here and here. Then we've got a straight line as we get back to the time axis again, and then we notice that continues until the line becomes flat again, or it looks like it's become flat at 175 seconds. We notice that 650 is positive, minus 125 is negative. How might we describe that journey? What about? The boat was at 50, the boat heads further away from the lighthouse, but it's decelerating until it stops 650 meters away. It remains stationary for a minute and travels back to the lighthouse, should have been to the lighthouse, at a constant velocity. And we could work out that velocity. We could work out the velocity by looking at the gradient. And there we've made the distinction between the curved part of the line and the straight part of the line. When it passes the lighthouse, it slows down. That's the steepness getting less until it stops. It looks like it's stopped 125 meters on the other side of the lighthouse. Right, find the velocity between 120 and 150 seconds. Right, a straight line between those two times. So the velocity is constant. Yeah. So the velocity at 121 seconds is the same as the velocity at 122, at 125, at 145. Between 120 and 150 seconds, the velocity is the gradient of the line, which is the change in y divided by the change in x, minus 22. The velocity is minus 22 meters per second. The average velocity, remember, average velocity is the change in displacement divided by time. The average velocity is the gradient of a chord. Put the chord in between 0 seconds and 175 seconds. The gradient of that line is minus 1 meters per second. Okay? The average velocity is the gradient of a chord, like we said on the previous page. Right, the next example. Okay, have a read of that example. Find the maximum velocity, the maximum speed. Okay, why don't we just work out the velocities everywhere? Okay, so between here and here, the velocity is, speed and velocity are not the same thing, remember that. Between there and there, the velocity is 6/3(2). Between here and here, the velocity is 0 meters a second. It's a horizontal line. Why am I doing meters per second with the slash in it? Because on PowerPoint I couldn't find the s to the -1. It doesn't matter. For the next time interval, now we notice that's a negative gradient, so the velocity is -1 there. For the next time interval, we get a velocity of -3. For the next time interval, we get a velocity of 1 meter a second. Maximum velocity is the velocity, well, it has to be positive. Positive velocities are bigger than negative ones. So it's 2 meters a second, which is that one. Now, speeds are the magnitudes of velocity. So even though this is the smallest velocity, change the sign to positive, it becomes the maximum speed. That is crucial. Reading questions carefully and not being fooled by that will be important. Speed and velocity are not the same thing. Oh, and then velocity at a particular time is not necessarily the same as average velocity in the same way that average speed isn't. Okay, the second sort of travel graphs we look at are the velocity time graphs. So if the gradient is the acceleration as it was at GCSE, and the area between the graph and the horizontal axis is the distance travelled. Now, hopefully, when we talked about it fitting with the calculus, how did we find distance travelled from velocity previously? We integrated. And what's an integral? What's a definite integral do? It gives you the area. So it's not a different idea at all. It's completely consistent with the calculus we've just done and the GCSE you've just done. The first example, there's a velocity time graph. If we want to find the acceleration during the first 30 seconds, we note that that is a straight line. In the next, between 40 and 60 seconds, that is a straight line. If you have a straight line on a velocity time graph, the acceleration is constant. If you have a horizontal line on a velocity time graph, the object is still traveling at a constant velocity. It's not at rest. So you've got to remember the difference between a horizontal line on a displacement time graph and a velocity time graph. Anyway, for the first 30 seconds, the acceleration is 0.27. Between 40 and 60, it's minus 0.4. It's accelerating. As the velocity increases, it's decelerating. But because they're both straight lines, the acceleration is constant there. When t is 60, so what happens there? The velocity goes from being positive, goes from being positive to being negative. But it also goes through 0 on the way to doing that. So it comes to rest, how long for? Momentarily, and then changes direction. Notice that for something we're going to look at, well, it's the same actually, we've just been looking at projectile motion, isn't it? Notice that for all of this motion, we had a positive velocity becoming 0, then becoming a negative velocity, and the gradient stayed the same. That would be the section of a velocity time graph that would show a projectile, wouldn't it? Because when you throw something up in the air and it comes down again, the acceleration stays the same. The acceleration is g all the way through. That was an aside. Distance travelled by the particle in the first 90 seconds. Distance travelled is the area between the graph and the time axis. Okay. Now we have two parts to the area. We have that part, which is a trapezium, and we have this part, which is a triangle. You need to be able to work out the area of both of them. Because it says distance, we just want the areas irrespective of sign. 280 and 90, 370. But if they had asked for us for the displacement, in the first 60 seconds it's 280. Between 60 and 90 it's minus 90. So the final displacement would be 190 plus 190. Displacement and distance travelled are different things. So next example, you can pause the video again and read the example. What do we want? We want a time graph. So here I've done the axes. What are we looking for? When t is 0, we have the velocity is 12, so we want 12 on the axis. Accelerates for 5 seconds with an acceleration of 1.2 until it reaches velocity capital V. It then travels at the same speed for t seconds, so that time from there to there is t, and then it then decelerates at 0.8, but we're not told anything about the times. Right, it can be difficult drawing straight lines like this, but I'll try. So it's got a constant acceleration for the first 5 seconds, so it's a straight line like that. It then travels with constant velocity, so we've got a horizontal line for t seconds, and then it decelerates at 0.8 meters a second, so this line should be shallower than the first one, so it looks like that. Okay, find the value of v. Well, two ways of doing it. Because we know the gradient is 1.2, we know v take 12 over 5 is 1.2. That gives us capital V is 50 meters a second. Or we could say that v, capital V, is the 12 plus 5 times 1.2 because v equals u plus at. But of course, those two things are simply rearrangements of each other. They're identical ideas. Nothing contradictory about those. Find the time that the car spends decelerating. Well, if we know the acceleration is minus 0.8, we've got change in velocity over time, which we can rearrange like that. Then the total distance travelled by the car is 600 meters. What is that on the graph? The 600 meters is all of that area. Okay, now that's a 5-sided shape, but I could divide it up into A1, this trapezium, so I'm going to call that area 1. I'm going to call that area 2, the rectangle, and I'm going to call that triangle area 3. So we've then got the area of the triangle is given by half base times height. If we take those away from the 600, we get that. So this rectangle must have an area of 322. It's got a height of 18. 1 divided by our 2 sig fig is actually 18 seconds. Right. Knowing that the area of a trapezium is that is helpful. Knowing that a trapezium can have a flat base and vertical sides and a sloping top is important. Knowing that a trapezium could look like 2 parallel sides and sides like that is important. Check that it really is a trapezium though when you're doing it. Notice our shape here had 1, 2, 3, 4, 5 sides. 1, 2, 3, 4, 5 sides. So that wasn't a trapezium at the beginning. Okay. Match up each velocity time graph with the corresponding displacement time graph. So what we got, what clues are there? I'm going to start with this one. We've got something with a velocity that's going down, but then a speed that's increasing. We've got something with a positive velocity, so it's traveling away. Then we've got something with a negative velocity, so it's coming back, which has to be going away but slowing down, coming back and speeding up. Those two go together. In this one here, the sector B, we've got a velocity that's always positive but getting less. So we're looking for something that's steep but getting shallower, but then finally the velocity is 0. So we're looking for a displacement time graph where it has got a 0 gradient. That is this one. Steep, getting shallower, finishing with 0 gradient. They go together. So this final one, yes, we know it must be C, but let's explain that. A velocity of 0, so a gradient of 0 at the beginning, finishes with a velocity of 0, so the gradient is 0 at the end, and between those 2 points we have increasing velocity, so a steepening graph, and then we've got decreasing velocity, so a graph that is getting shallower. And this point here nicely is actually called a point of inflection, but we don't have to do that. Right. Exercise 18C is very good. There's a lovely progression of questions which nicely explore all the ideas. It's a good, important topic. I'd like my group to submit 5, 7, 10 and 14. Can you check with your teachers where they'd like answers submitted? Post questions on Edmodo, because I'm not the only person checking that. I know Mr. Holloway at least has put comments on to that as well. We'll all answer comments for people. Once we've looked at the problem solving in section 5, the final bit of this, we'll set a task. We might use some or all of next week to consolidate all the kinematics. Okay. Then we've still got a big section. The kinematics is a very important section. The kinematics is one of the key sections. The next bit we do, the work with the forces, with the statics and the dynamics, is another one of the big key sections. Right, enjoy that work. I'll see you on the next video.